Okay, so maybe it's a time. So our next speaker is Professor Bálint Virág from University of Toronto. His great work on random matrix, determinantal process, and random walks has earned him the Rollo Davidson Prize, Collector James Prize, and John Singe Award. He was an invited speaker of ICM, and he will present the directed landscape. And the paper with the same title was also awarded Frontiers of Science Award this year. So let's warmly welcome Professor Virág.
Thank you very much for the opportunity. Can you turn the volume down a little bit? Just a little bit lower? Thank you. Okay, so I'm giving a board talk, so there is some options here. How many of you are in probability? Raise your hand. How many of you are not in probability? And maybe in geometry? Anybody in geometry? Oh, yeah, just here, okay. Please. Yeah, let me take it off. It's far, just not used. It's far to record my screen. Okay, like that? Maybe better. Okay, so the topic here is directed landscape. A directed landscape is what's called the universal central object in this KPZ class. The KPZ class, I won't talk to you a lot about KPZ equation, but one way to think about the KPZ class is that it's random planar geometry. And so what do we mean by this? There's, of course, many ways to do random planar geometry. You'll see some other ways than mine. Here, what we're interested in is some kind of perturbation of Euclidean geometry in the plane. And then what is the perturbation? The perturbation we usually want to be local and independent at different places. So if you go far away, then the perturbation should be essentially independent. There are many models of these. You can imagine your own model. You can imagine a continuous model, for example, where you say randomly drop points in the plane and change locally the metric in the plane, or you could just think of first passage percolation where you put weights. So take the integer lattice with the edges and make the lengths random. And then you have a metric space, and you would like to understand this metric space. So these are really beautiful models, and none of them we can understand. Okay? So we would really like to do these models, first passage percolation especially, and we cannot do them. So even though we believe they are in this class, we don't know how to prove it. Okay, nevertheless, we expect that everything will behave as other models in this class. And then how other models behave together is summarized in this central object called the directed landscape. So let me tell you first the definition of what this is. Okay, so the definition that I'm giving you is not the one in the paper. This paper, by the way, that the prizes for was a construction of this object. And my goal today is not so much to talk about the construction, although maybe that will also come up in the end, but more like just to give you some ideas of how this object is and how you work with it. How do you prove things? What are the questions that you're asking? What are the tools? Okay, so that's going to be the main thing is just to familiarize yourself with what this is and how to use it for proving things. Okay, so the definition is the following. So you're going to define it as a scaling limit, okay? And it's a scaling limit of a discrete model, which is very much like first passage percolation with a little bit of a difference. And this is called exponential last passage percolation. So I'll just write LPP. So what you have here is the even lattice. Okay, it's just the lattice points where the sum of the coordinates is even. And to each such lattice point, assign an exponential random variable, okay, rate 1, and they're going to be all independent. Okay? And now your goal is to define a so-called distance or the last passage time between 2 points. Just fix 2 points. Okay, look at all the possible upright paths, okay, and maximize their length. So the maximum length is going to be the distance. What is the length? Well, the length is just the sum of all the exponential weights on the vertices. Okay, so you see it's not exactly like a distance because you're maximizing instead of minimizing, but because you can only consider upright paths, this actually makes sense. You can make it infinity by going around many times. Okay, and it turns out that this will be a model that for some reason we can actually understand. Okay, so if you have 2 points here in the plane, P and Q, I already defined this distance. Okay, so it's the maximal over path, the sum of the weights over the path. And the length of the path is, of course, just the sum of the weights. And a geodesic is a path that actually achieves this maximum. So when you do simulations of this object, you can, for example, take this to be 0, and you take this to be 0, n for some n even. Okay. Then you will see that you can always find some geodesic, and what the simulation will show you is that the amount that this geodesic goes to the left and right is about n to the 2/3. Okay. So what that tells you is that if you sort of want to understand the geometry before this whole process, you have to consider a scaling window in which in one direction you see about n, and the other direction you go to about n to the 2/3. Okay, and one question, for example, is that you have this random continuous function, right, which is the geodesic. You rescale this in some way. Will this have a limit? So will this be some kind of limiting random continuous function defined on 0, 1, starting at 0 and ending on 0? So in the classical setting, we try to understand, for example, Brownian motion as the limit of random walks. Then you can do this by considering, finite dimensional distribution. What is the distribution at a given time? And then those things converge, so then the process converges. Unfortunately, we don't have any access like this in this setting. So instead, what we do study is kind of the entire metric, and this entire metric does have a limit in this specific case. Let me tell you what the limit is. So now we're going to look at D. Okay, so let's first of all look at one thing. So if you could look at D00 to 0n, okay, with n even, if you just take a fixed path, right, and you sum the exponentials, they're of mean 1, so typically the mean will be of order 1. The typical path will have length n, right? But we're not looking at the typical path, but we're looking at the length, the maximal path. So that actually is a theorem that if you divide this by n, it's going to converge to a number greater than 1, as you expect. In fact, it's going to converge to 2. Okay, so that's kind of the first thing that you can look at. Another thing that you can look at, and this was done by Johansson in the 1990s, is you can look at this object, so just the distance, and subtract this to n, right? So see what are the fluctuations. So now you get something which is little of 2n. And in fact, the answer is it's of order n to the 1/3. So Johansson proved that if you divide this by 2 times n to the 1/3, then this converges, and now this was an almost sure convergence, this was a convergent law. Okay, and it has a limit, which is the GUE trace-of-Inham distribution, also known as the limiting distribution of the top eigenvalue of a random Hermitian matrix. So that's this is Johansson from the 2000. But what we're interested in is we'd really like to capture this geodesic, and just from a single distance, that will not be enough. So we will actually put in a bunch of parameters. Okay, and then the goal is to look at this. So we're going to look at D. Okay, and we're going to have, so first this will be space and this will be time. Vertical is time. Okay, so we're going to go from ns to nt in time, Okay, so I'm going to put in, and then the horizontal fluctuation has to be n to the 2/3. We're going to have an n to the 2/3, and y and t. Okay, and then I'm going to have to put here a 2. That's just some classical reasons. I think maybe that's not needed there. So I'm looking at these points whose macroscopic coordinates are x and s and y and t, but then they're blown up into this window, scaling window that I talked about. So you subtract from it the typical value, right? And the typical value was this 2n, but now you go from s to t, so you get 2n times t minus s. Okay, and then again, you divide by 2 times n to the 1/3, and this converges in law to a random 4-parameter function, L of x, s, y, t. Okay, and this random 4-parameter function is called the directed landscape. Now, this is a definition, but it has a typical problem. It's not obvious that such a limit exists. So there is a lot of work, and in fact, this isn't how we originally defined the object. I will tell a little bit more about the construction, but at least it's a definition. It's mathematical. Okay. So let's see what kind of object do we have. So this was a bit like a distance. Here, negative L is going to be a bit like a distance. So for example, this object satisfies the triangle inequality with the opposite sign, just because of maximizing over paths. It's a straightforward consequence. So this object will also satisfy the triangle inequality. In fact, something stronger. So the metric composition. So let me tell you what it is. So if you want to go from P to Q, because these are 2 points, and you have some intermediate time here between P and Q code T, then if you want to understand L of PQ, so the distance between P and Q, then this is equal to the maximum over X of L going from P to XT plus L going from XT to Q. Okay, and what this represents is, first of all, it has if you remove the maximum, you just get the triangle inequality. You get an inequality that is triangle inequality. And it also represents that there was a geodesic, just like in the original place. There should be a geodesic, and then in this geodesic, when you achieve this distance, you actually should have inequality. You should have an equality for this thing. So this is metric composition. Some other properties. One of them is scaling. So this is called the K-Physics scaling. That just comes from the fact of how we got this as a limit. This kind of scaling limits, they always have to be scale invariant. And the scale invariant is the following thing. So if I look at L of, let me see, so maybe put a cubed t, a cubed s, and a cubed t, and you put a squared x and a squared y, and then you divide by a, okay, then it has the same law as L, okay, as a function of x as y. So it has this kind of self-similar fractal property. So that's 2 properties. Of course, it also has the symmetries inherited from this lattice, like you can shift and so on, and those symmetries are still around. Let me tell you one more thing, which is the distribution. So just like Brownian motion, its fixed time distribution is, up to some scale and shift is essentially the same at every time. So the law, you look at L xs by t, and it's equal in law to t minus s to the 1/3 times the Straits-Widom law. Okay, so that's the fluctuation term. Minus, there is a term which is called the Dirichlet norm. So this is x minus y squared t minus s. This we call d here, okay, which is a kind of mean term. Okay, so this x minus y squared over t minus s has the following interpretation. Okay, so if you just took not this random metric that we had, but you took the Euclidean metric and you applied to it the same scaling. Okay, and in the scaling limit, you see the circle, but the only thing that you pick up from this is the quadratic term. You would get this t. Okay, this is a 4-parameter object, exactly in the same scaling as we applied to the exponential s passage. Okay, so you should think of this as some kind of memory of Euclidean space in some sense, and this is the memory of the randomness. Now, of course, these trace-Vidom laws are very intricately coupled all over the plane. They're not independent at all. Because their distances and the paths interact. So if you go far away, then they become independent. Typically, they are not. And another thing that we kind of see is that we have lost the environment itself. So remember, we had IID random variables, and in the limit, we don't have any of those anymore. Okay, so we just have some kind of aggregate of that embedded in this L. Okay. So what are the properties that we use to study? So first of all, let me just write that this part, we denote R, and then this thing we call D. Okay, so this is deterministic, and this is the random form over here. Okay, so the properties that we use to study L, the main properties are actually most of the time the probabilistic story is just the following. One of them is the trace-Vidom tail bounds. So if you want to understand this random variable, you can ask what is the chance that the trace-Vidom is greater than some a. Okay, and this is you're interested in when a goes to infinity. And there's a nice formula for this. In the top part, it has a sub-Gaussian tail. So this is the exponential of minus 4/3. This is right, of a to the 3/2 plus little 1 times a to the 3/2. Okay, and the probability that the trace-Vidom is less than some minus a is exponential of minus 1/12 plus little 1 of a to the a cubed. Okay, so you have this trace-Vidom tail bounds. This is what we use to understand this metric, and then we have a beautiful result, which is a combination of a lot of work, starting with work by Corbin and Hammond, and then some extra work afterwards by Hammond himself. But eventually, Duncan Lilburn proved the following thing, which is that if you just look at L, okay, and let's look at starting from some fixed point for simplicity. So let's say you start from 0, 0. Okay, and then I'm going to look at what is this distance at time 1, but at some arbitrary location x. Okay, so this is now just a function of x. Okay. If you draw this function, it will look a bit like this. You remember there was a parabola in there. There's a Dirichlet part, so that's what you're following, and then there is a random trace-Vidom part. But if you restrict it to some interval, say 0, x0, okay, so this is now a random functionally compact interval, and subtract from it value at 0, 0, 0, 1. Okay, then this is absolutely continuous with respect to Brownian motion with bounded Radon curve. So if you're not a probabilist, the way you should think about it is that we can understand the structure of this as x varies through Brownian motion, which is something that we know infinitely more than anything in this area. So basically, essentially anything you can ask, we can answer about Brownian motion. So these are the two things that I want to use. And let me just give you a few corollaries. Okay? So these corollaries are probabilistic. So what you do is you take this input, which comes from some integrable world, okay, and take this input, which is Euler's theorem, and just do some standard probabilistic arguments, which are actually not too difficult. And you can get some nice properties of L, okay? And so I want to say two things. One of them is bound on R. Okay, so this is, remember, the random part here. So what you get is that R of xs by t is less than or equal to some random constant. Now there is, remember, it's a trace of idem part, so it should have a t minus s to the 1/3. Okay, and then afterwards you have to include the fact that there are many scales and so on, but because the tails are exponential, these only contribute a logarithmic factor. So in fact, you get a log to the 2/3 times, something like the norm of x syt. And I think you have to put here plus the norm of plus 1 over t minus s, something like that, and the random constant. So you have a bound on R, which tells you that, first of all, on bounded sets, this R is actually uniformly bounded, so it's not a huge perturbation of the Dirichlet norm. Notice that the Dirichlet norm itself is not bounded on bounded sets. When T and S get close to each other, this can be very big. Right? But R doesn't get bounded, so it's kind of nice. Sorry, I just put absolute value. So this is like L1 norm of x y t. Okay, plus that. And then the second thing is I'm going to be a little bit sloppy here. Is a modulus of continuity bound. So if you look at L of let's x1 s1 y1 t1 minus L of x2 s2 y2 t2. In fact, maybe I put it for the R's because the other part is easier to handle. So let's put it for the R's. Then you can bound this. And so what do you get? So first of all, you're going to have some Hölder type norms. In the x direction, because of the Brownian motion, you get something like x1 minus x2 to the 1/2. Right? That's just the Brownian thing. Plus y1 minus y2 to the 1/2. Okay, in the spatial direction, because of the 1/3 scaling, you get an s1 minus s2 1/3 plus t1 minus t2 to 1/3. Okay, and then I'm just going to say a random constant times some log terms. Okay, too many things to write, but essentially some log terms. So you should think about this as this is just what you get from the scaling. This is just there is nothing more than what you get here from the scaling, and then there's just some extra log term that account for many scales. And all of this is, very standard argument. If you're probabilist, then it's similar to how you prove Kolmogorov-Chantsov just by single point bounds. It's just a little bit done differently because you need a little bit more precision than in Kolmogorov-Chantsov. So these are things that you just prove from these bounds. It's not more. So let me tell you a few more things of what this can be useful. And for this, I want to define two things. So one of them is, so let's just define path lengths in geodesics. Okay. So what is a path? Well, a path is just going to be a continuous function from an interval. So st to r, and we're going to call it pi. Okay, so that's what the path is. Okay, so how do you define the length of a path with respect to directed landscape? This is just a very standard definition from metric spaces, essentially. The length is simply, so the length of pi is just going to be the, you see, the infimum over all subdivisions. So you take t0 equals t, as then t1, tk equals s. Okay, and then you're summing, and this is also the infimum over k. So you're summing of I equals 1 to k, right, of L of, let me just cheat a little bit and write it as pi of ti minus 1 to pi of ti. Right, so you take the path, you divide it up into pieces, add these distances, and then take the infimum over all divisions. When you further subdivide something like this, then you get monotonicity. That's because of the triangle inequality. So it's actually very nice when these things always exist. And a very nice exercise, by the way, that actually follows from what you have seen. Okay, so the constant pi, so pi from 0, 1, r, pi of t equals to 0. Okay, so just the vertical line has minus infinite length. Okay? So pi, let me put L here to say that it's directly next to minus infinity. I guess one thing I forgot to emphasize is because we remember you subtracted some mean, this L can take positive and negative values. But for most of the cases, this actually isn't such a problem. It's not so important in studying these metrics to have the distance positive. Okay, so in fact, every fixed path with probability 1 will have minus infinity length, so it's not going to be nice, but there are going to be random paths that take values that whose length is nice. And so that's the length, and then the geodesic is just defined as, you know, the pi. So it is a PQ path. So PQ path just means that it goes from P to Q when we draw it. So the graph is going from P to Q. So pi is defined as pi length is equal to LPQ. So that's when we call a path geodesic, when it actually achieves the distance. Yeah. Good question. So it's going into R, okay? And then the way you think about it in R2 is that you think of the graph of the function, right? So the path will not backtrack. Remember, this is the limit of last passage percolation, which is oriented. So you're already there, the path didn't backtrack. And the surprising thing is, or maybe the first time you think about it, the surprising is even when you want to take the limit of first passage percolation, where you're allowed to backtrack, in the limit, the paths are expected not to backtrack. So there's always going to be this kind of, so the things that have finite length will always be just graphs of functions and also just graphs of very special functions. Are they unique? Very good question. That's exactly what I was going to study now. Okay. So let's see. Where are we? So now we define what geodesics are. And one thing that we don't yet know, although you can prove this by taking the limit, as we did, is whether geodesics exist, right? It's not, even that is not clear. And the main clue to that is basically two things. So let me just give you a brief overview. So one of them is that so fix P and Q here, and then so those are 2 points. Then it's not so hard to check that if you look at all paths between P and Q with at least some length. Remember, the good paths here have big lengths, bad paths have small lengths because of the change of sign. So bounded lengths paths, they stay in a compact set. And if you think about it, the proof of that is just the following. If you went really far away, okay, then remember the length was kind of an infimum. So you could just take this subvision, that would be actually a bound, an upper bound on the length of your path. But this path will be bad because you have to go here. That gives you a terrible Dirichlet distance. Remember, there was an x minus y squared, so it's quadratic. But the r term is only grows logarithmically, so it's not gonna compensate for that. So because of that, it's very easy to check that this is true. Okay, and the second thing is that, in fact, even cooler. So bounded length paths have a uniform Hölder 1/2 norm. Okay. So in fact, they have uniform Hölder bounded let PQ paths have uniform Hölder 1/2 norm. I will also, maybe I'll give you the proof of that if we have, yeah, I think we have enough time, so I'll give you the proof of that. And if your probability used to Hölder 1/2 minus because Brownian motion has that property, here this isn't Hölder 1/2 minus, they're actually Hölder 1/2. So every bounded length path, it cannot be too rough. And by the way, maybe tell you the fourth one, the third one, which I'm not going to, but it also follows deterministically from what I have shown you already, so these modulus of continuity, which is the geodesics. That's not true for bounded length paths, but it's true for geodesics. Are Hölder 2/3 minus. Okay, so they're actually quite regular. This, by the way, tells you that they don't look anything like Brownian motion. And Brownian motion assigns 0 mass to anything, but this is so regular. So it's a very different world. This one again is just follows from what I've already told you, and I won't tell you. But this one is easy; it's just one line. So let me tell you. Okay, so the idea is just follows from the triangle inequality. So you look at LPQ. So here's the picture, right? So I'm going to have my P and Q, and then I have some bounded length path here, okay, between P and Q. I'm gonna pick 2 points here. Let's say x1, s1, x1 and x1, and this is x2 and s2. Okay, and I want to have some kind of further bound on this. Okay? And so what I do is I just write L of PQ, right, is less than or equal to what's happening here. Well, there is L of P xs1 plus L of x1 s1 L of x2 s2 q plus L of x1 s1 x2 s2. Right, this is just a triangle inequality. Yeah, other direction. Thank you. 6 square chairs are equal to that. And so what you do is gonna write this as R plus D, R minus D. Okay. You argue that this and this has to be bounded, and the R has to be bounded because this path, remember, these bounded length paths, they have to stay in a compact set, and R is bounded in a compact set. So you can rearrange, and you just get a lower bound on D, right? And what is D here? Well, there's just x1 minus x2 over s1 squared over s2 minus s1, right? And it's less than or equal to something bounded. Okay, and if you see, this is exactly a Hölder 1/2 bound. Does this make sense? So you argue this is bounded, and the R here is bounded, so you just get an upper bound on D, and the upper bound on D is actually exactly a Hölder 1 bound. That's right, so the amount that this path can change, x1 minus x2 squared, is bounded by s1 minus s2 without square times a constant. So that's just exactly a Hölder 1 bound. So you see that's nice. Okay. And so one of the things that you get from this automatically is that geodesics exist. And the way you prove that geodesics exist. There are many ways to prove it, but one way to do it is that you construct them point by point. So here is your P and Q. Okay, you look at halfway. Remember, a metric composition allows you to pick your point such that the distance to here plus the distance to here is equal to the total distance. You pick that point, okay, and then you go again halfway, pick a point here. Okay, and so keep going half time, pick more and more points. But what you know when you pick these points is what you're constructing is uniformly Höder. Okay? So therefore there's a limit, and that's a geodesic. So we have shown that geodesics exist. Okay, so let me tell you that geodesics are unique. That was the question. Okay, so this actually just follows from the metric composition. So let me write it for the 0001 geodesic, but actually it doesn't matter. So you write that L, okay. So to show that the geodesic is unique, right? It's enough to show that it's unique at every fixed time with probability 1. Because if that's true, then it's unique at every rational time with probability 1 just by a union bound. And then the geodesic continuous functions are determined by the advised rational times, right? So why is it unique at a fixed time? Well, where does the geodesic go? Well, so if you go from P to Q, right? Here's a geodesic and here's some T. Then you get that the geodesic location X, this is where it goes, let's call it X. So this was the argmax, right? Of L of, what was it? P to xt plus L of xt to Q, right? That was the argmax of these two things. That's where the geodesic has to go. Otherwise, you have a strict triangle inequality, and you're in trouble. The point cannot be on the geodesic, right? So remember that this thing, when you restrict it to a compact interval, is essentially a Brownian motion, at least absolutely continuous to that, which means that all the almost sure properties are carried over. Okay, so whatever is true for Brownian motion with probability 1, also true for this guy with probability 1. And this is actually an independent Brownian motion here, right? Because this part just depends on the lower half of the plane. That part just only depends on the upper half of this. And you remember that was independent before you took a limit, and that independence is inherited. Okay? So these two are just absolutely continuous with two independent Brownian motions. Okay? And so you just have to prove that when you took Brownian motion and restrict to a fixed interval, any fixed interval, and you have to take take union bound over bigger and bigger intervals, then the maximum is unique. Okay, so that's a beautiful exercise. If you haven't done it, I recommend. Brownian motion does have a unique maximum. So this implies that geodesics are. Okay, but interestingly, the only thing that you get out of it is that if you have two fixed points P and Q, then geodesics are unique between this P and Q. Okay? And then it generalizes, of course, to almost all points just by a Fubini, or say all rational points just by a union bound, but it's not actually true for all points. Okay, so there's a question of how many points can you get from how many geodesics between strange points in the DI. Okay? And there is a theorem due to Duncan, which says that the number of geodesics that you see over all points is always the same set. Okay? So you just look at all the numbers that you get, and this set contains 1, it contains 2, it contains 3, it's 4, 5, 6, 7, 8, 9, but not 10. So that's the answer. The number of geodesics is anything between 1 and 9. And if I have enough time, I can show you up to 121. But I'm not sure about that, so let me just tell you a little bit about how do you prove this thing. Okay? and also how do you argue in this world to get some result like this? Okay? And the first step in here is actually a quantitative version of this theorem. Okay, so we're just asking if you have P and Q that are fixed, what is the number of maxima? But if you want to be able to vary P and Q, then you have to do the following operation. Instead of studying actual maximizers, you have to study near maximizers with some epsilon put in there. Okay, and you have to see how the probability of having K near maximizers decays in epsilon. It's going to be some power of epsilon. In fact, that's just the Brownian motion fact, and the probability that there are K epsilon near maximizers. So you know what that means, right? It's just things that are at least the max minus epsilon for a Brownian motion, and therefore also in this setting is about epsilon to the K minus 1. So for when it's 1 up to some constants. When it's 1, it's not decaying, there's always a maximizer, but when there's 2, and it's like that. And then what you do is you kind of, you want to show this for many, you're going to fix some time. Again, it's enough to understand rational times. And then you're going to move P and Q around. And then this epsilon to the K minus 1 has to fight with how many places you can move P and Q to. So basically, define little boxes, and in little boxes of P and Q, this story doesn't really change, and they just have to count how many little boxes there are. Now, how many little boxes are there? Remember from the KPZ scaling, right? When we scaled values by epsilon, we had to scale the time by epsilon cubed, okay? And they had to scale space by epsilon squared, right? So the number of boxes, this is the size of the little box. The number of little boxes to cover some complex set is this, but there are 2 endpoints, so you get squared. Okay? So this probability has to be this one. Okay? So therefore, you get actually that they get the following thing: that if you look at any point in the projected landscape, P and Q, and you look at any time between, and you look at all the geodesics that go between P and Q, and then you count the number of places that it intersects this time, the number of times. So that's less than or equal to 11. Okay? That comes from the fact that you have to beat this 10 by this K minus 1. So 12 doesn't, if you do 12, that's too big. 11 is still possible, at least according to this argument. Okay? So you have that. But you see what this gives you, it doesn't really give you how many geodesics there are. It just tells you that at a given time, you can see at most 9 different places where they go through. They could still like do some kind of dance where they unite and split and so on. Okay? But I want to tell you why this thing doesn't happen. And it follows from 2 theorems, and both of them are beautiful. The main input that is needed here. Okay, so let me tell you one thing. And then this is the following. So let's take that you take a geodesic, gamma, and you look at a geodesic gamma prime, which is unique. So it's a unique geodesics between these endpoints. And we look at how these geodesics can intersect. Okay? So what is the intersection? We define the set of intersections as the set of times away from the endpoints, so the endpoints are not included, such that these 2 things are equal. Okay? So that's their overlap. That's called the overlap. Okay, and if gamma prime is a rational endpoint geodesic and gamma is a general geodesic, then what I claim is the overlap has to be an interval, possibly empty. So why cannot be 2 intervals? Why can it be that this goes away like this? Do you see the argument? Does anybody see the argument? Why can gamma prime do this? Or why can the overlap look like this? Anybody sees? So remember that you have to use that gamma prime is a unique geodesic, right? So if you had a detour like this, then of course you could replace this part of gamma prime by this pi of gamma, and you would get a different geodesic for gamma prime, right? But there is unique, so it cannot happen. Okay, so this is one statement. Overlap is an interval. And this is true if this is a rational geodesic gamma is a general, but in fact, there is a proof, and I may not be able to say too much about it. I would like to, that shows you that this is actually true for any two geodesics. Okay? So generalized. So let me see, 15 minutes. So let me maybe delay the proof of this. Okay, so let me show how this generalizes. This is actually a little bit difficult. This part I'm putting under the rug. It's not an easy part. So far, I think everything else I put in was more or less under the rug, was more or less doable. So how does this tell me? How can I now bound the number of geodesics between 2 points? Okay, so now remember, if I want to say that there are at most, 200 geodesics between 2 points, it's enough to show that when I restrict those geodesics to, the starting time plus epsilon to the end time minus epsilon, there are at most 200 of them there, because then you just let epsilon go to 0. Right? So let's argue that point. So now you have a bunch of geodesics, and they can do things, they can split and so on. This kind of thing they can actually do. And so you look at the time epsilon and minus epsilon, or plus epsilon and epsilon away from there and there. And well, one thing that you know is what you see here, is there are at most 11 points. Right here, what you see that we have proved that. And also here, you have at most 11 points. Again, same story, right? But if I know a geodesic where it goes here and I know where it goes here, between a point here and a point here, they could be only a unique geodesic. Why not? Why is that? Because if we had two geodesics, right, then I would have this geodesic bubble, which is exactly the thing that we argued against here. Geodesics bubble don't exist because then you could switch and then you could switch geodesics, and that would give you a counterexample. So this tells you that between any of the, if you pick a point here and pick a point here, you see at most one geodesic between these 2 points. There are 11 points here, there are 11 points here, so there are at most 121 geodesics between any 2 points. Okay, so that's just a little bit of how you work with this directed landscape. I want to tell you a little bit more about this story. This is actually a result of Duncan and some of it by Mana and Batia as well. So we actually know exactly how many geodesics exist. Okay, so there could be 1 to 9. And when you draw, as you see, when you draw geodesics, they also form some kind of graph structure. Okay, this graph structure is called the geodesic network. And Duncan has proved that there are exactly 27 geodesic networks. So I'm not going to give you a full list of pictures, but I'm going to tell you the special ones which exist between 2 fixed times. Right? So if you fix your times in advance, you'll have fewer special properties. And so for fixed times, you just see fewer networks. In fact, you see exactly 5. And I'll show you the ones that you see. So you just see single geodesic. That's one option. You can actually see 2 disjoint geodesics, except for the endpoints. So that's another option. Then, we're in Canada, so you see here a canoe paddle. Okay. And then you see also a kayak paddle, which looks like that. Okay. And then you see a shield. We call this a shield, which looks like this. Okay, and in terms of number of geodesics, this says 1, this is 2, this is 2, this is 4, and this is 3. So these are the ones that you see between two fixed times. But, between general times, there are far more of them. Okay, so let me tell you a few open problems. Maybe I'll skip this proof here, but let me tell you a few open problems here. One nice problem that we don't know and we would like to understand is do geodesics have a description by themselves? Can you describe a geodesic without an environment? It's just like Brownian motion, you describe it by doing distributions. We don't even have a nice enough formula for a single point distribution of a geodesic. We have a formula, but it has an infinite sum in it, unfortunately. So it's a probability law. But if you want to understand, at 2 times, T1 and T2, then we don't have a formula for that. Again, one question that we don't understand is, let's say that I give you the shape of the geodesic. So you see where the geodesic went. Okay? Can you tell the length of it just by looking at the shape? Is this question clear? Right? So the shape is not necessarily a function of the length. We don't know. So does shape determine length? So that's one open problem. And finally, let me tell you a theorem that is part of the universality story. And this has to do with kind of the classical history of this last passage percolation and random permutations. So let's take a random permutation on n numbers. Okay, so something like 9, 2, 7, 4, 6, 8, 3, 1, 2, 3, 4, 5, 6, 7, 1. What's missing? 5. Okay, and then you can look at increasing subsequences. Right, for example, 3, 2, 3, 5 is an increasing subsequence, and you can look at the longest increasing subsequence in the random permutation. So the length of the longest increasing subsequence was a classical problem called Ulam's problem, and Bagdieff and Johansson in 1999 showed that after you remove the mean, which is by the 2 root n, the length is the mean, or it's essentially the mean, then it converges to a trace of Vidom law. Okay, but you can study something else, which is not just the length, but the longest increasing subsequence itself. Okay, so let's call Ln to be the longest increasing subsequence as a list. Okay, so we're going to look at so you can think of this as a random function. Okay, so list, and you can plot the list as a function. And so this actually has a scaling limit. So if you look at Ln at 2t, this is going to be the parameter that we're showing, square root of n. Okay. So typically, when you went to about t fraction of the total length of the longest increasing subsequence, the value that you see is roughly n times t. That's not surprising, because this increasing subsequence is roughly equally distributed. So if you subtract this and want to see what the fluctuations are around this value, then the right object to divide by is 2 times n to the 5 6. Okay? Right, so now we have a random function for every n. And this is kind of a random step function corrected by some linear function. So this is this random function, and this converges to, in law, to gamma of t as a random continuous function, which is the geodesic in this random metric in 2 dimensions. So this is one of the results where you see universality of KPZ and random geometry. And you don't see geometry here because geometry is a little bit hidden, but that's true for ordinary geometry as well, right? Quite often it's not completely obvious that there's geometry, but there's a geometry problem behind. And there are lots of hidden geometry problems. For example, maybe that's not so hidden, but another place you see KPZ universality and the directed landscape we proved recently is in the stochastic heat equation. So you look at the multiplicative stochastic heat equation in 2D. Okay, so the delta U, right? So it evolves as half Laplacian plus some white noise here. Space-time, no, it's just spatial white noise. So this is not time dependent, spatial white noise. Okay, so you imagine of heat spreading in some kind of random environment. Then what we had found that in the large deviation regime, so when you go really far and there is little heat there, then you see an entire KPZ universality there. So there is actually an entire directed landscape hidden in this equation, even though a priori you can't really tell that just from looking at the equation. Okay. So I have one more thing to say, which is I really wanted to understand this gamma, right? This geodesic that we discussed during this lecture. And I was hoping that there'll be some simple description of the law. And we don't really have a simple description, but here is something that is a little bit negative. Okay? My student Dennis Spivak was studying the large deviation of this directed geodesic. So what you're looking at is what is the probability that gamma t, so gamma is going from 0 to 1, okay, we're going from 0, 0 to 0, 1, is greater than or equal to r. We're looking at as r goes to infinity, okay? And we actually managed to compute this, there's some answer to this. It looks like this. So it's exponential minus r cubed. So it's actually it doesn't really like to fluctuate too much. It's like exponential minus r cubed. But the interesting thing is the constant. So the constant is 8 plus O1 over 3a cubed, 3t cubed, 3 minus greater to 8t. And this is for t between 0 and a half. Okay, so there's some complicated but explicit constant here. And this may be not the most interesting thing, this constant, but what's really interesting is where does this large deviation come from? And why is the constant so complicated? So I have a short answer to that. And the answer is, you can ask, okay, let's say that I want this geodesic to be greater than r at some small time, say t equals 1/10. You may ask the question is, what is the geodesic going to do under this requirement, right? So how is it going to look like? So we're used to Brownian motion, large deviations, and what you expect is this kind of the geodesic goes to here, and then it just comes back, okay? That's what Brownian motion would do. It would just go back in straight line. Unfortunately, when you do this thing will not be a geodesic because there'll be shortcuts here. So it's not the right thing to do. So in fact, Danny has studied this and solved the variational problem. And in fact, what this geodesic will do is, here's t, here is 2t. And it's actually going to go further away a little bit, okay? And afterwards, it's still going to go further away, do a parabola, come back to here. So this is what the large deviation event makes the geodesic behave like. So it really sort of tries to avoid having these shortcuts, and in fact, it goes much farther than it has to be at other times than the times that we wanted it to be far from 0. So this kind of shows you that the geodesic behavior is probably not super simple. Even large deviations are not super simple, and that's kind of usually what we can understand the best. So that's it. Thank you very much.
Any question from the audience?
So do you know if two geodesics can meet at exactly one point?
Um,
I'm asking that because everything's analogous to the Brownian map, and that's been kind of a surprisingly frustrating thing to rule out there.
yeah, I don't know. So yeah, the interval could be 1 point a priori. I think the answer is no, but I don't have the proof.
And then for the length being determined by the shape, should it just be like the Minkowski content or something like that?
It's more subtle than that. Yeah, it's not. I don't think it's symmetric. So one thing that we proved is that when you look at the geodesic, remember for Brownian motion we have quadratic variations. So you break it up into small pieces of equal size, you square them and you add them, and then you take a limit and you get the time of the Brownian motion. So the geodesic has the same thing with 3/2 variation. So the 3/2 variation is equal to the time. We proved that. No, it's a little bit harder. There are some partial results though. So Duncan has proved that if you know all the geodesic shapes in the directed landscape, that determines all the distances. So that's known. We have some improvement on that with Mastuzzi, that you just knew some kind of an infinite sequence of geodesic trees to infinity that already tells you all the distances. And so there are a few things like that that we know. But for a single geodesic, this is still low.
Have you studied the geodesic, what you call the geodesic networks with k points instead of 2? And try to classify, let's say 3 points, and I look at all geodesics connecting these 3 points.
Geodesic networks with k points. Oh yeah. So you could, yeah. So I didn't get to this point, but this is actually how we actually constructed the directed landscape. Is you can study the following objects. So you look at two disjoint paths, okay, and you want to maximize their length. They have to be disjoint, and this is related to the RSK map. Because the Green's formulation of RSK map is actually exactly that. So it's in fact just the RSK map in this setting, RSK for Robinson-Shenstedt-Knuth. And yes, so no, these haven't been classified. You need a brief soul to do that. Even for just 2 points, you get 27. So
Yes.
So you said that there are other models of random geometries that are not understood. Does this model give at least some conjectures for them what should be true there?
yes, so in fact, the conjectures are extremely simple. The conjectures are all those models converge to this directed landscape. And so therefore, all these phenomena that I told you about are present in every single one of those models. So this phenomenon is present in some way in the stochastic heat equation, which is a completely different story. Present in some way in random permutations, and so on. So anything you prove about the directed landscape has some analogy in any model that converges to it.
So all of these things are now conjectures in that.
Yeah, so the universality conjecture, of which we do very, very little, essentially nothing. We can only prove, I think the only models that we can prove that converge to the directed landscape are either things that have, where we can understand the law of the RSK map, I can't explain that, or some geometric version or perturbations of those slight perturbations. So there is some amount of perturbation we can do and understand, but no.
So basically say that in any reasonable random geometry, you have at most 9 geodesics.
No, that's not quite the right translation. So the translation is a bit more subtle than that, but yeah.
Okay, so